2.2, day 3. Our topic is domain and range. So you probably remember a few key facts about domain and range from Algebra 2. Specifically, domain is the x values, and range, that's the y values. So x is domain, y is range. Therefore, domain must be the independent variable, and range represents the dependent variable. Okay, so quick example to start us off. Here's a function q equals f of t, and that's all I give you, just q equals f of t. So I want to know what you would identify as the domain and what you would identify as the range. So to me, the domain, that's the inputs. So here's how I read this. Q is a function of t. So t is our inputs. So those t's, whatever they are, times, maybe they're 1 hour, 2 hour, 3 hour, those are our inputs, whatever the t's are, the times. And then our outputs, there's one or two ways you could say it. So you input the t, and you could say the output, your answer, is the q, so the q's, or you could also say the f of t's. So either the q's or the f of t's. Either way is fine. Inputs, the t's, outputs, q's, or f of t's. In fact, just think about this equation. It says q equals f of t, so that should be okay. So domain, that's our input value, and then the range, those are our output values. So let's get a formal definition down here. So for domain, which is our inputs again, I'll say it again, that's our inputs. That's the set of all inputs, the set of all input values which yield an output value. So the set of all the input values which yield an output value. They're special. And so for the range is just the set of those output values. So the set of output values. So we're going to evaluate domain and range both graphically and algebraically. First, we need to review interval notation a little bit. So you should have seen this in Algebra 2. Two types of brackets or parentheses. This one I'd call the closed bracket. This one's the open bracket. So when I think about the closed bracket, to me I'm thinking that's where things are equal. So if I put this on the end of my interval, that means that number on the end is actually in the interval, it's equal. Or if you think about it on a number line, it would just be a closed dot, like it's included in the interval. It's included in the number line shading. So in words, I call this a closed bracket. So for this guy, this is the open one. You could probably guess what I'd put to correspond to each piece here. Instead of equal, it's not equal. Instead of closed circle, it's an open circle. So essentially, if you see the open bracket on the end of your interval, that means that that point at the end of the interval is not included in there. So that's for open brackets. Okay, so when we construct these things, we read them from left to right. So it's always smaller number on the left, bigger number on the right. So left to right always. Whether it's two closed brackets, two open parentheses, or you could have a combination of the two. So you could have one open, one closed, right? Just either way, you could have a combination. And then one quick note I want to make about brackets regarding infinities. So if you're at infinity, like the domain or the range just blows up and it goes off and it has no end, we just got to be sure that we don't use those closed brackets, because you can never actually equal infinity or negative infinity. So if you can never equal those things, you can never actually grasp infinity or negative infinity, then we should always use the open brackets, for the infinities. So that actually should all just be a little refresher from Algebra 2. You should be familiar with interval notation. So let's put these intervals to good use. So example 2, part A. X is between 3 and 7, and it's less than or equal to 7, but it's greater than 3. So how's that going to look at an interval? Well, let's consider the number line first. So if you sketch a number line, 3 and 7, and I know X is between there, so you can represent all the numbers in between there too. So I'll shade that. But the question is, what kind of dots, closed or open circles, go on the 3 or the 7? Well, since the 7's included, that gets the closed dot, and the 3 is not included, so that's one gets the open dot. So number line, pretty straightforward. So in my mind, in terms of the brackets and parentheses, I'm just going to draw right over these. So if it's a closed dot, that means it's included, that gets a closed bracket. If it's an open dot, it's not included at that point, that gets the open bracket. So I just draw it right over the top of them. So I'm not going to illustrate that for all these, but in my mind, mentally, that's what I'm thinking, that's what's going on. So I got 3, 7, and I got the open bracket on the 3, the closed bracket on the 7. Okay, so for part B, x is greater than or equal to -4. That's all you got. So all the numbers bigger than or equal to -4. Well, since we read domain and range intervals from left to right, smaller number, bigger number, -4 is going to be the smallest thing in there, and everything else should be bigger than it. So -4 is on the left, and that's a closed bracket because it's included. And then all the numbers bigger than -4, that just goes off to infinity. Okay, so part C, y is less than 6. So right away you know 6 is the biggest number, so it would be on the right side of the interval. And all the numbers less than 6 would go off to negative infinity. Last but not least, part D, that R thing right there. So that's a symbol for the real numbers. So all real numbers, and none of the fake ones, all real numbers. So that's the infinities, right? The lazy eights, from negative infinity to positive infinity. That's how you represent that in interval notation. Okay, so for example 3 here, I'm just going to make a little graph here. I'm going to sketch something. So I'm going to put a few points down. I'm going to go -2, 2, 1, -1, and 4, 3. -2, 2, 1, -1, and 4, 3. Then I'm just going to make the sketch of this graph. It's kind of funky looking. Looks like a piece of maybe a curved parabola and then a piece of a line. So maybe it's a piecewise function. But the equation of the function doesn't matter. Just get the graph, -2, 2, 1, -1, and 4, 3. So the question I'm going to ask has to do with domain and range. So what's the domain? What's the range? Okay, so if you know the domain represents the x values, where does this thing live on the x-axis? What x values does it take? So you'll notice there's not arrows on the ends of this. So it has definite defined endpoints there and there. It doesn't go beyond that. So we won't be talking about infinity for this one. This one does not go to infinity. So for the domain, I'm going to represent it with some arrows here. When I think about it, I'm thinking the spread on the x-axis, how far does it go from left to right? That's the domain. If you look at this guy, in terms of the x values, it never goes below -2. That's the endpoint, it stops. And it never goes above 4 for the x value. So that will be our domain. It's just a question of, is it open or closed brackets? Well, since the -2 is included, it's closed. Since the 4 is not included, it's open. So that's how I visualize domain. It's just how far are we across the x-axis. So what about the range? So for the range, we know that's up and down. How high does it go? How low does it go? And again, there's no infinities here. It's got definite defined endpoints. So for the range, I'm going to do that in orange here. Up and down, where does it live? Well, it looks like the highest it would ever go would be 3, that point right there, but it's not included at 3. And then the lowest, looking like -1 for the lowest y value. So the -1 gets to be included, whereas the 3 is not included because it was an open circle. It's not included at that point. So example 4. F of x equals x squared minus 5. So you should know essentially what the graph of this thing looks like. It's quadratic, so it's just a parabola. And in fact, it's just a parabola shifted down 5. So if you take this x squared and subtract 5, it's literally just the parabola you would think of, plain old parabola, and then move it down 5 on the y-axis. So let's make a quick sketch of that. Notice I just ticked off 5 tick marks here, going down 5 on the y-axis. And I'll just sketch the general shape for a parabola. So again, What's the domain? What's the range? Okay. Well, if you think about the x values this thing takes, I think you can pretty much plug in whatever you want for x. There's no limitations. In fact, the arrows are kind of pointing off to the right and pointing off to the left. This suggests it could go to infinity above and below. So again, I'm going to illustrate it with the pink arrows here for domain. How widespread is it? When we look at the trend, the arrows are getting wider and wider and wider if they keep going on that path. So this actually goes from negative infinity to infinity. And for the range, right, the up and down, the y values, now this one's definitely not negative infinity to infinity. Yeah, I'll agree it goes to positive infinity, but it certainly doesn't go any lower than negative 5. So for the range, that's negative 5 to infinity, and notice the negative 5 is included. Okay, so example 5. How about h of x equals negative 2 plus x? H of x equals negative 2 plus x. So what's special about this graph? It's a square root function, I know. If you remember what a square root function looks like, it's like half a parabola that's been twisted and turned onto its side. So what happened to this? Instead of being just plain old square root of x, there's negative 2 inside there. So another way you could think of it is just, you could have called that square root of x minus 2, right? And then maybe that now you know what the transformation was. This was the square root function that got shifted to the right 2. So I'm going to just erase that. This is a square root function that shifted right 2. So what's the domain for this guy? Well, let's make a quick sketch of it. Again, I don't need very many tick marks here. I'm just going to take my square root, my half a parabola, and shift it right 2. That's good. And then let's talk about what the domain and range are. Half a parabola kind of just laying on its side there. So for the domain, again, the pink arrows, how widespread is it? Well, it certainly never goes below 2 on the x-axis, and it never goes, well, there's no limit on how high it goes, right? In terms of the x values, it'll go off this way for infinity. That's where the arrow's pointing. It's going trending that way. So 2 is included right there. It hits that point, and then off to positive infinity for the domain. Okay, so how about for the range? I'll go orange arrows again. So for the height of this graph, yeah, I'll agree that the trend for the arrow pointing up, it's going to go up to positive infinity, so there's no upper limit on it. But there's definitely a lower limit, right? It'll never go below 0 for the y value. Look at that point. It's the lowest point on the graph. It'll never go below 0. So for the range, it goes from 0 to positive infinity. Okay, so that's just 2 examples of how we can read these things from graphs. And this year we're going to be able to read them from our calculator as well. The graphs on the calculator. Okay, so let's talk about some domain issues, some problems we might have, otherwise known as restrictions. First one, first issue that will cause us grief and problems, square roots. So square roots only take a certain kind of numbers, if you recall. In fact, you know one thing for sure, they can't take negative values. So you can't take the square root of a negative number. That's the whole point. And it's a little sad. I'm sorry. Wish you could, but you can't. Sorry. Doesn't make sense. So you can't take the square root of a negative number. So when we talk about the domain, what our restriction is, we need to have an expression inside the square root. Inside the square root that's greater than or equal to 0. So the expression inside the square root, the little green cloud here to represent that, the thing inside the square root that you're taking the square root of, that's got to be bigger than or equal to 0, right? That means positive or non-negative. So no negative numbers in there. Okay, so let's look at a little example here. Example 6. F of x equals the square root of x plus 3. So what's the domain for that? Okay, so without looking at the graph, there's going to be a restriction on this because there's a square root. You know you can only have positive numbers in here inside the square root. So what kind of numbers in this case would cause us problems? Well, let's just take this x plus 3 piece and say x plus 3, I know you have to be greater than or equal to 0, right? That's how I set it up. I know that thing inside the square root has to be greater than or equal to 0. So this is actually pretty simple to solve. Subtract 3 on both sides, and then what do you know about x? X has to be greater than or equal to 3. Negative 3, excuse me. X has to be greater than or equal to negative 3 if you solve that. So the domain, all the numbers bigger than or equal to negative 3, is just negative 3 to infinity. So this one's fairly simple to evaluate if we have a square root. Look inside the square root, that expression, the x plus 3. We know it had to be bigger than or equal to 0, so we just solve this for x. X is greater than or equal to negative 3, so there's our interval, negative 3 to infinity. And once you get used to it, by the way, writing these things in interval notation is much nicer than using inequalities, especially when we have multiple pieces to it. Okay, another relevant example for us. How about f of x equals the square root of x minus 2 plus 4? Okay, so it's important to identify why we would actually have restrictions on this. Why would we actually have restrictions on this? Well, this 4 right here is not causing us any grief. It's really not bothering us. Right? I don't care. It can do whatever it wants. The only beef I have is with the stuff under the square root. I know that that stuff has got to be positive. I can't take negative numbers in there. So for starters, that 4 there, that doesn't create any restrictions, any issues. So if the 4 doesn't create any problems, let's focus in on what does create problems, that x minus 2 piece. So if we know that thing's got to be greater than or equal to 0, right away that implies that x has got to be bigger than or equal to 2. Anything less than it, and you'll start getting negative numbers in there. It's no good. So our domain, from 2 to infinity. To get further confirmation on our answer, if you've got your calculator handy, you can always graph to check these and make sure the graph agrees with your algebraic result here. But this one I think we can graph pretty easily just by analyzing a little bit. So if you have a minus 2 inside the function with the x, that's what shifts it right 2. And then a plus 4 out here by itself, that shifts the graph up 4. So I can actually make a rough sketch right now of this square root graph that got shifted right 2 and then up 4. So yeah, if you look at that domain, the x values from 2 to infinity, yep. And now you could actually kind of observe the range here too. It looks like that'd be 4 to positive infinity. Okay, our second beef, our second issue or restrictions with domain come when we have fractions. I'm not talking about just any kind of fractions. I'm talking about fractions with variables in the denominator. Those are no good for us as far as domain goes sometimes. So, what's the problem? If you have an x in the denominator like so, well, there's one number you know you can't divide by. You can never let x be 0 because you can't divide by 0. Again, sad, sorry, 0. That's just not a thing. So if you got a variable in the denominator, that's no good because you can't divide by 0. So that'll create a restriction for us. So far we've got square roots, there can't be negative numbers in there, and we've got fractions with variables in the denominator because that can never be 0. So how do we deal with this? If we know the denominator should never be 0, we can just solve the bottom piece here. For this example 8, take a look at this. So g of x equals 1 over x plus 3. So there is going to be a restriction because we've got a variable in the denominator. And there's a certain kind of x you could plug in there that would make that denominator 0 out, and that would be no good. Because anything divided by 0 is undefined. It doesn't exist, nor does it make sense. Okay, so that's our job to find out where that value is going to take place. So if we take that x plus 3, we know that piece in the denominator can never be 0. So I just set it up this way. x plus 3 cannot equal 0. Well, you could actually solve this really easily to know what x cannot be. Subtract 3 on both sides, what do you know? You already know that x can never be 3. And in fact, if you make the graph, it looks like this. So if I make 3 tick marks, 1, 2, 3, I just put a dotted line straight down through it, and then it has these curves that just go in the corners here with the x-axis and this dotted line here at -3. That's actually called a vertical asymptote, if you remember from Algebra 2. So that's what the graph of this thing looks like. It's called the reciprocal function. So -3 doesn't exist. If it did, you would think it would be a 0 here somewhere, but nope, it doesn't exist. It gets really close to this line but never touches it. So what's the domain here? So we know that x can be pretty much any real number you want. All real numbers, anything you want in the entire world, except it can never be -3. Because that's when you would get a 0 in the denominator, and that'd be no good for any of us. So it can be all real numbers except -3. So how do we say that with interval notation? So there's two pieces. It gets broken up. So look at my little arrows here. I'm going back to use the pink arrows. Domain, all these x values, and then all these x values, but you notice where the break is, -3, where you couldn't have an x. So how do I do that? Well, think about what this interval is representing. This pink arrow on the left here. So this is actually everything negative infinity all the way up to this -3. And then there's a break in the graph. Can't be -3. And then this arrow on the right here, that picks it back up. That comes back at -3 and goes all the way off to positive infinity. So there's two pieces of this domain. For the left-hand piece, that's negative infinity up to -3. And then the right-hand piece would be -3 to positive infinity. And notice I put open parentheses on this -3, right? Because it can never actually touch it. You get as close as you want, but you can never actually touch it. Okay, so to group these together, from negative infinity to -3, and then from -3 to infinity, put this big U thing in the middle. Put that big U thing right there. That represents union. So this piece, union with this piece. And that's how we deal with breaks in the domain. So that first pink arrow, negative infinity to -3, there's a break, and then it picks back up at -3, goes to positive infinity. Since we have two broken pieces, we'll just put union in the middle. And while we're on the subject, let's talk about what the range would be for this graph. So back to the orange arrows here. If you follow where the graph lives, it's got a piece of the range up here with this curve, and then a piece of the range down below with this curve. But it looks like it just gets really close to the x-axis and never touches it, which is true. So for the range, the top piece, that's 0 to infinity. The bottom piece, that was actually everything below, so negative infinity all the way up to 0. So that's actually a broken range too. So we know the y values can never be 0, so it can never exist here. So that's where our break is. So from negative infinity to 0, union with 0 to infinity. And again, note the open parentheses I have on the zeros because it doesn't actually hit that point. It gets really close to it, but never touches it. Because our y values can actually never be 0. So the output can never be 0. Okay, example 9. 9 of 10, one more after this. So here's a function, c of x equals x plus 9 divided by x squared minus 2x. So if I ask you about domain, there should be an alarm go off in your head because you see variables in the denominator. The ones on top I don't worry about. They don't bother me. The ones that bother me are the ones in the denominator. So we know we're going to have restrictions in that sense. So we start talking about domain, you got to look at that denominator and say, when will that thing be 0? Because that's where I'm going to be restricted. Okay, so How do you solve that at 0? So x squared minus 2x can never be 0. Little weird, right? But if you're good at factoring, this actually becomes a lot easier. You can factor GCF factor an x out of both of these terms. And what are you left with? X minus 2? Oh, so now you've got x at 0 and x minus 2 at 0. So you've got your two answers right here. What do you know about x? So x can't be 0 and x can never be 2. If you don't believe that, try plugging those values in right now. 0 squared minus 2 times 0, yeah, not going to work. So the two values x can never be, since we just factored it and solved it at 0. X can never be 0, x can never be 2. But it can be whatever else you want, just not those two things. So we say it can be all real numbers except 0 and 2. So on a number line, how's that look? You can shade everything that you want, more the merrier, except you can never have anything at 0 and 2. So the reason I talk about the number line here is because we're going to have that broken up domain again. So you have this piece from negative infinity to 0. So this piece right here, from negative infinity to 0. Then there's a break at 0. Then you got this piece from 0 to 2. So union with the piece from 0 to 2. And then you got another break here at 2. So that's union with the piece, everything up above 2. So 2 to infinity. 2 to infinity and beyond. So that is our answer for domain. Notice it got broken up twice, so it actually split it up into 3 pieces here. But that's our solution for domain here. All right, last example for these notes. Example 10. 10 good ones today. D of x, some function, equals 3x squared minus 11. So again, I'm going to ask domain and range. But what you should know is if there's no restrictions on this, really, nothing going wrong with this guy. There's no fractions of the variable in the denominator. There's no square roots. So there's no restrictions on this graph. So if there's no restrictions in general, this is just a plain old polynomial. In fact, it's a quadratic binomial if you want to get specific. But for any polynomial like this that doesn't have weird stuff going on, like square roots and variables in the denominator, you should just know that the domain is going to be all real numbers, negative infinity to infinity. So as long as there's no funny business, we expect the domain to be all real numbers. I can't say the same for the range, but in terms of the domain, you could plug in whatever x value you want, positive, negative, 0, and this thing will take it. Here's the graph, just a rough sketch. It's a parabola shifted down. So domain, yeah, you can plug in whatever you want for x. The arrows trend out right, trend out left. Definitely there's a lower bound here for the range, but domain, negative infinity to infinity. All right, that's all I got for you today. Have a good one. I'll see you in class.